There's something humbling about looking up at the night sky, isn't there? Those pinpricks of light scattered across the darkness have sparked wonder for as long as humans have walked the earth. But here's the thing, what we see with our eyes is just the tiniest fraction of what's really out there. The universe is hiding secrets, layers of mystery tucked away in the folds of space and time, waiting to be uncovered. And right now, we're living through a revolution in how we explore those secrets. Cutting-edge technologies are giving us eyes where we once had none, ears where there was only silence. Gravitational waves ripple through the fabric of reality, whispering stories of colliding black holes. Quantum telescopes peer into the void with unprecedented clarity, revealing cosmic oddities that defy imagination. This isn't just about new gadgets, it's about rewriting the very story of the cosmos, one discovery at a time. Think about it, for centuries, astronomers relied on light alone to understand the universe. But light can only tell us so much. It's like trying to piece together a symphony when you've only ever heard the violin section. Now, with advancements like neutrino detectors and space-based observatories, we're finally hearing the full orchestra. We're detecting particles that journeyed billions of years to reach us, carrying messages from the far reaches of existence. We're mapping dark matter, probing the edges of black holes, and even catching glimpses of phenomena that shouldn't, by our old understanding, be possible at all. The universe is stranger, more vibrant, and more mysterious than we ever dared to dream. So, what does this mean for us? It means we're standing on the brink of a new era of cosmic discovery. Every breakthrough peels back another layer of the universe's best-kept secrets, challenging what we thought we knew and opening doors to questions we haven't even thought to ask yet. This journey isn't just for scientists in labs. It's for anyone who's ever looked up at the stars and felt that tug of curiosity. And that's exactly what we're diving into today, how these incredible technologies are reshaping our place in the cosmos and what they might reveal next. Buckle up, because the universe has surprises in store, and we're just starting to uncover them. For most of human history, the universe was defined by what we could see with our own eyes, a canvas of stars painted in visible light. Early astronomers like Galileo turned simple telescopes toward the heavens and marveled at the craters of the moon or the rings of Saturn, but even those revolutionary tools had limits. The truth is, visible light makes up just a sliver of the electromagnetic spectrum, like hearing only one note in an endless symphony. Countless cosmic phenomena don't glow in ways our eyes or even traditional telescopes can detect. Take black holes, for instance. By their very nature, they swallow light entirely, leaving behind only eerie distortions in the fabric of space. Or dark matter, which doesn't interact with light at all, yet its gravitational pull sculpts entire galaxies. These hidden forces shaped the universe while remaining utterly invisible to us for centuries. The challenge wasn't just technological, it was perceptual. We built tools to extend our senses, but they were still rooted in the same narrow slice of reality we evolved to perceive. Imagine standing in a pitch-black forest, listening for creatures in the night. You might hear rustling leaves or distant owl calls, but you'd miss the ultrasonic pulses of bats or the low-frequency vibrations of elephants miles away. That's what early astronomy was like. We were deaf to the universe's full chorus. Even as telescopes grew more powerful, they were still, metaphorically, straining to hear whispers in a language we didn't yet understand. This blind spot had consequences. For generations, astronomers puzzled over galaxies spinning faster than their visible mass should allow, or strange gravitational tugs with no apparent source. The answers were right there, hidden in the dark. It wasn't until the 20th century that we began developing instruments sensitive to the universe's other languages: radio waves, X-rays, gravitational ripples, each revealing a new layer of the cosmic puzzle. Suddenly, the invisible became tangible. radio telescopes uncovered quasars blazing from the edge of time. Infrared sensors pierced dust clouds to witness stars being born. And that's the real revelation. The universe wasn't hiding its secrets out of spite. We just needed to learn how to listen. So what changed? The shift wasn't just about building better tools. It was about rethinking what observation even means. Light, as it turns out, is just one messenger. The cosmos speaks in neutrinos, in warped space-time, in the faintest heat signatures of ancient radiation. Every breakthrough in detection technology is like gaining a new sense, allowing us to read pages of the universe's diary that were once blank to us. And with each page, the story gets stranger, richer, and more humbling, because the greatest lesson here isn't just about what we've found, it's about how much more awaits just beyond the edge of our perception. In 2015, humanity crossed a threshold we'd dreamed of for a century. We heard the universe speak for the first time, not in light or radio waves, but in the subtle shudders of spacetime itself. The Laser Interferometer Gravitational Wave Observatory, or LIGO, caught the faint echo of two black holes colliding over 1 billion years ago, a cataclysm so violent it sent ripples across the cosmos at the speed of light. Imagine dropping a pebble into a still pond and watching the waves spread. Now picture that pebble as an object 30 times the mass of our Sun, and the pond as the very fabric of reality. That's what LIGO detected, a distortion so tiny it stretched a 4-kilometer-long laser beam by less than 1,000th the width of a proton. The sheer audacity of this technology is staggering. LIGO and its European counterpart Virgo don't look like traditional telescopes at all. Instead of lenses or mirrors, they use laser beams bouncing between precisely aligned mirrors in massive L-shaped vacuum tunnels. When a gravitational wave passes through, it minutely alters the length of these arms, creating an interference pattern scientists can decode like a cosmic fingerprint. It's as if we've built a microphone sensitive enough to hear the rustle of a single leaf in a hurricane, and then used it to eavesdrop on the birth cries of black holes. What makes this revolutionary isn't just the engineering marvel. For the first time, we're observing the universe through something other than electromagnetic waves. Before LIGO, black hole collisions were theoretical ghosts hidden behind curtains of impenetrable darkness. Now, we're piecing together their stories from the wrinkles they leave in space-time. Each detection unveils details no telescope could ever see: the precise masses of the colliding objects, their spin rates, even the way they warp their surroundings in those final violent moments. One particularly striking event in 2017 wasn't black holes at all, but two neutron stars merging. Telescopes worldwide swung into action, capturing the accompanying flash of light, marking the first ever multi-messenger astrophysics observation. Suddenly, we weren't just hearing the universe, we were cross-referencing its diary entries. The implications are profound. Gravitational waves carry pristine information, unaffected by the dust and gas that distort light. They're giving us front-row seats to phenomena we couldn't previously study, like intermediate mass black holes or the possible existence of cosmic strings, hypothetical defects in spacetime left over from the Big Bang. Every chirp and thrum in LIGO data is rewriting astrophysics textbooks, and this is just the beginning. Future upgrades and next-generation detectors like the space-based LISA mission will extend our hearing range even further, potentially revealing whispers from the universe's first microseconds. We've spent millennia staring at the cosmos. Now, at long last, we're learning to listen. While gravitational waves opened our ears to the universe's hidden symphony, another revolutionary tool is sharpening our vision beyond anything we've known before. The James Webb Space Telescope, launched in 2021, isn't just an upgrade, it's a paradigm shift. Nestled a million miles from Earth, this engineering marvel sees in infrared light, piercing through cosmic dust clouds like night vision goggles for the cosmos. Where Hubble showed us the universe's portrait, JWST is revealing its fingerprints, uncovering details we never knew to look for. Infrared light is the key. Unlike visible light, which gets absorbed or scattered by dust, infrared waves slip right through, carrying secrets from the universe's most obscured corners. It's the difference between trying to watch a bonfire through thick smoke versus feeling its warmth on your skin. JWST-18 gold-plated hexagonal mirrors and ultra-sensitive instruments capture this warmth, translating it into images of breathtaking clarity. Already, it's spotted galaxies so ancient their light has been traveling for over 13 billion years, snapshots of the universe in its infancy. These aren't just distant specks, they're cosmic toddlers, defying expectations by appearing more structured and mature than our models predicted. But JWST isn't just about peering into the past. It's revolutionizing how we study exoplanets, worlds orbiting distant stars. By analyzing the starlight filtering through their atmospheres, the telescope can identify molecules like water vapor, carbon dioxide, even potential biosignatures. Imagine holding a prism up to a street lamp and deducing the chemical composition of a window it passed through. That's the precision we're talking about. One early target, the gas giant WASP 96b, revealed clouds of silicate, essentially sandstorms raging in an atmosphere hotter than lava. Perhaps most astonishing is JWST's ability to make the invisible tangible. Nebulas that appeared as hazy blobs in older telescopes now unravel into intricate tapestries of gas and newborn stars. The pillars of creation, iconic from Hubble's images, take on new life under JWST gaze, every dust filament and stellar nursery rendered in eerie, glowing detail. It's like switching from a charcoal sketch to a high-definition hologram. This telescope isn't just filling gaps in our knowledge, it's redrawing the map entirely. Every image challenges assumptions, whether it's surprisingly heavy early galaxies or complex organic molecules swirling in planet-forming disks. The universe, it turns out, has been busy, building, evolving, and hiding wonders in wavelengths we couldn't previously access. With JWST, we're not just observers anymore. We're time travelers, forensic scientists, and cosmic cartographers all at once, rewriting the story of everything with every new snapshot from the void. Dark matter is the universe's most frustrating magic trick, an invisible force holding galaxies together, bending light around cosmic corners, yet slipping through every net we cast to catch it. For decades, scientists have known it must exist. The math demands it. Stars whirl around galaxies too fast, clusters behave as if tugged by unseen hands, and the cosmic microwave background bears its fingerprints. But how do you study something that refuses to glow, reflect, or collide with ordinary matter? The answer might lie in technology so precise it borders on the surreal. Quantum sensors capable of detecting the faintest whispers of the unseen. These aren't your average detectors. Quantum sensors exploit the bizarre rules of quantum mechanics, where particles can exist in multiple states at once until measured. Imagine setting up a grid of dominoes so finely balanced that even a ghost's breath could topple them. That's the principle behind devices like superconducting qubits or ultra-cold atom interferometers. They're engineered to react to disturbances smaller than a single electron's nudge, disturbances that might finally reveal dark matter's elusive particles. One leading candidate, WIMP, weakly interacting massive particles, could bump into atomic nuclei with barely a whisper. Traditional detectors might miss it entirely, but quantum sensors amplify that whisper into a shout. The stakes couldn't be higher. If dark matter interacts even faintly with normal matter, these sensors could catch it in the act. Projects like the Super Cryogenic Dark Matter Search, buried deep underground to shield from cosmic noise, cool their detectors to near absolute zero where quantum effects dominate. Others, like the action dark matter experiment, hunt for hypothetical particles that might briefly click, like a radio tuning into a faint station when exposed to strong magnetic fields. Each experiment is a high-stakes gamble, probing different corners of theory for a payoff that could rewrite physics. But here's the twist: the longer dark matter evades detection, the more creative the hunt becomes. Some scientists now suspect it might not be a single particle, but an entire hidden ecosystem, a dark sector with its own forces and particles. Quantum sensors could be our first window into this shadow realm. Picture explorers not just mapping a new continent, but realizing they've stumbled upon a parallel world overlapping our own. The implications ripple far beyond cosmology. Quantum sensing technology, refined in this extreme pursuit, is already spilling over into medicine, navigation, and materials science. It's a reminder that the tools we build to chase the universe's biggest mysteries often unlock revolutions closer to home. And that's the beauty of this quest. Even if dark matter keeps dodging us, the hunt itself is bending the limits of what's possible, turning the invisible into the inevitable. There's something almost poetic about neutrinos, these ethereal particles that slip through planets like they're made of mist, carrying messages from the most cataclysmic events in the cosmos. Born in the hearts of exploding stars, the fury of black holes, and even the Big Bang itself, neutrinos are the universe's most discreet couriers. Every second, trillions pass through your body without a trace. Catching them isn't just difficult, it's like trying to trap sunlight in your hands. Yet, against all odds, we've built machines that do exactly that. Take IceCube, the most ambitious neutrino observatory on Earth, a telescope unlike any other. Buried deep in the Antarctic ice, it transforms a cubic kilometer of frozen water into a particle detector. When a neutrino does collide with an atom, an event rarer than winning the lottery, it spawns a streak of blue light called Cherenkov radiation. IceCube's thousands of embedded sensors capture this faint glow, tracing the particle's path back to its violent origins. It's astronomy, but not as we know it. Instead of gazing upward, we're peering through the planet itself, using Earth as a shield to filter out cosmic noise. The data is revelatory. In 2013, IceCube detected neutrinos with energies millions of times greater than those produced in particle accelerators. Their source, likely supermassive black holes in distant galaxies, spewing jets of matter at near light speed. Then, in 2022, another breakthrough. A neutrino linked to a flaring galaxy 4 billion light-years away, its light and particle arriving in tandem. For the first time, we could correlate a neutrino with a visible cosmic explosion, a Rosetta Stone moment for multi-messenger astronomy. But neutrinos aren't just messengers from far-flung disasters. They're time capsules. Solar neutrinos, for instance, take just 8 minutes to reach Earth from the Sun's core, but they were forged in nuclear reactions hundreds of thousands of years ago, when the photons we see today were still fighting their way through the Sun's dense interior. By studying them, we're effectively reading the Sun's diary entries from epochs before human civilization existed. Even more tantalizing are relic neutrinos from the Big Bang, a faint background hum that, if detected, would give us a direct window into the universe's first second. What makes neutrino astronomy so transformative is its defiance of cosmic censorship. Light gets absorbed, bent, or obscured by dust and gas. Gravitational waves reveal collisions, but little about their environment. Neutrinos, they travel unscathed, delivering unfiltered dispatches from places no other signal can escape. When a star goes supernova, its neutrinos arrive hours before the light, offering early warnings to telescopes. In the chaotic cores of active galaxies, they might carry clues about how black holes power their monstrous jets. The challenge and the thrill is that every detection is a cosmic detective story. Unlike the steady stream of light from stars, neutrinos arrive as individual puzzle pieces, each demanding meticulous interpretation. Future observatories, like the planned cubic-kilometer neutrino telescope under the Mediterranean, will expand our net, potentially catching neutrinos from sources we haven't even imagined yet. We're learning to listen to the universe's quietest whispers and, in their faint traces, finding echoes of the unimaginable. Imagine trying to drink from a fire hose of cosmic data. That's the challenge modern astronomy faces. Every night, telescopes worldwide capture petabytes of information, flickering stars, shifting galaxies, the faint whispers of distant worlds. There's simply too much for human eyes to process. Enter artificial intelligence, the unsung hero of 21st century discovery. Machine learning algorithms now comb through this avalanche of data with superhuman precision, spotting needles in cosmic haystacks that would take astronomers lifetimes to find. Take the hunt for exoplanets. NASA Kepler mission alone identified thousands of potential worlds by detecting the subtle dimming of stars as planets pass in front of them. But buried in that data were false positives, stellar flares, dust clouds, instrument glitches. Training AI to distinguish these imposters from genuine planets has supercharged the search. One neural network, fed decades of Kepler observations, recently uncovered 50 new exoplanets in old data, including rocky worlds in the habitable zone. The algorithm didn't just confirm known patterns, it learned to recognize anomalies human researchers had missed. Then there's galaxy classification. The universe teems with galactic oddities, colliding spirals, cannibalistic ellipticals, rings that defy physics. Sorting them manually is like trying to catalog every grain of sand on a beach. But AI doesn't just classify, it discovers. In 2019, a team at the University of Hertfordshire trained an algorithm on simulated galaxies, then unleashed it on real telescope images. The AI promptly flagged bizarre, red spirals, galaxies that shouldn't exist according to prevailing models. Turns out, their star formation had mysteriously halted while their spiral arms persisted, rewriting assumptions about galactic evolution. Perhaps most astonishing is AI's predictive power. At the University of Toronto, researchers built a system that simulates cosmic structure formation in milliseconds, a task requiring supercomputers weeks to complete. Other models now forecast solar flares before they erupt or predict when distant supernova will brighten, giving telescopes precious advance notice. It's as if we've taught machines to read the universe's playbook before the ink dries. But here's the beautiful irony. AI isn't replacing astronomers, it's making them more imaginative. Freed from drudge work, scientists now ask questions too complex for any algorithm. The Vera Rubin Observatory, set to begin its survey next year, will generate 10 terabytes of data nightly. Without AI, we'd drown in the deluge. With it, we're poised to uncover asteroids, supernova, and phenomena we haven't even named yet. The future of cosmic discovery isn't just human or machine. It's the alchemy of both, rewriting the rules of exploration one dataset at a time. Radio astronomy strips the universe bare, revealing its hidden scaffolding in ways optical telescopes never could. While our eyes perceive a scattering of stars and galaxies, radio telescopes expose the grand architecture beneath, a cosmic web of gas, dust, and magnetic fields stretching across unimaginable distances. Take the Atacama Large Millimeter Array, or ALMA, perched high in Chile's desert. Its 66 antennas work in concert, capturing whispers from cold hydrogen clouds and the birth cries of planets. But the real marvel isn't just the sensitivity, it's the scale of what these instruments unveil. Galaxies aren't isolated islands, they're nodes in a vast filamentary network, connected by threads of gas so thin they'd make a spider's silk seem stout. This is the cosmic web, the universe's underlying skeleton, and radio telescopes are our cartographers. By tuning into the faint hum of hydrogen, the same element forged in the Big Bang. We've mapped these tendrils across billions of light years. It's like discovering that every city on Earth is linked by invisible highways, bustling with unseen traffic. Some of the most startling revelations come from the web's darkest corners. Pulsars, the lighthouses of the cosmos, beam radio waves with metronomic precision. These spinning neutron stars act as cosmic clocks, their rhythms distorted only when gravitational waves ripple past. Then there's the mysterious dark flow, clusters of galaxies drifting toward some unseen attractor beyond our observable horizon, a hint that the web might extend farther than we ever imagined. But perhaps no discovery is more profound than the cosmic microwave background's polarization, imprinted when the universe was a mere 380,000 years old. Radio telescopes like the South Pole Telescope read these faint patterns like tree rings, revealing how the infant cosmos's quantum fluctuations inflated into the web we see today. It's forensic science on a universal scale. What makes radio astronomy so transformative is its ability to see the unseeable. Optical light blinds us to the cold, the distant, the obscured. Radio waves slip through, carrying tales from the universe's quietest corners. Every new frequency scanned unveils another layer, another thread in the tapestry. And as arrays grow more powerful, we're not just mapping the web, we're learning how it pulses with life, channeling the raw material for stars, planets, and perhaps one day living worlds. The hunt for life beyond Earth has shifted from science fiction to hard science, and the key lies in the very air alien worlds breathe. For centuries, the question of whether we're alone lingered in the realm of speculation. Now, with cutting-edge spectrographs dissecting the light filtering through exoplanet atmospheres, we're closer than ever to an answer. Imagine holding a prism to a sunset and decoding the chemistry of a distant continent from the colors alone. That's the power of these instruments. They don't just spot planets, they taste their skies, sifting starlight for the faint fingerprints of molecules like oxygen, methane, and water vapor. Take the James Webb Space Telescope's early discoveries. When it trained its sights on WASP 39b, a gas giant 700 light-years away, it didn't just confirm the planet's existence, it mapped its atmospheric layers, spotting carbon dioxide and sulfur dioxide swirling in a scorching, unbreathable haze. This wasn't just a technical feat, it was proof that we can profile alien weather systems from interstellar distances. But the real prize lies in rocky worlds like those in the TRAPPIST-1 system, where future observations might catch the subtle imbalance of gases that screams life. Here's why oxygen is such a smoking gun. On Earth, it's a byproduct of photosynthesis constantly replenished by living things. Detecting it alongside methane, a gas it normally destroys, would suggest an active biosphere keeping both in circulation. It's like walking into a room where a candle burns steadily despite an open window. Something must be relighting it. The extremely large telescope, set to see first light in 2027, will take this search to new heights. With a mirror 39 meters wide, it'll capture spectra from Earth-sized planets in habitable zones, scanning for combinations of gases that defy geological explanation. But biosignatures are tricky. A lifeless world with volcanic activity might mimic life's chemical cues, while alien biology could produce signatures we've never thought to look for. That's why next-gen tools like the Habitable Worlds Observatory will cross-check multiple clues, not just gases, but surface features like vegetations, red edge, reflectance, or industrial pollutants. The search has become a cosmic forensic investigation, piecing together evidence one photon at a time. What makes this moment so electrifying isn't just the technology, it's the stakes. Every atmospheric analysis is a step toward answering humanity's oldest question. And with each new instrument pushing the limits of detection, we're not just searching for life anymore. We're learning how to recognize it when we see it, even if it's nothing like we ever imagined. For all its vastness, the universe is far from static. It's a stage where cosmic dramas unfold in real time, often too quickly for traditional telescopes to catch. Time-domain astronomy has turned this challenge into a revolution, transforming how we study the sky's most fleeting spectacles. Imagine trying to photograph lightning with a camera that takes hours to snap a single picture. Until recently, that's how astronomy worked. We'd point telescopes at patches of sky and wait, missing the explosions, collisions, and eruptions that define the cosmos's most violent moments. Now, thanks to networks of robotic telescopes and algorithms that react faster than human hands, we're finally keeping pace. Take gamma-ray bursts, the universe's most powerful explosions. Lasting mere seconds, these bursts outshine entire galaxies, yet by the time astronomers manually trained telescopes on their coordinates, they'd often vanished. Enter systems like the Rapid Telescopes for Optical Response, or ROTSI, which swing into action within seconds of a satellite detecting a burst. These robotic eyes capture the afterglow, revealing details about the burst's origin, often a collapsing star or colliding neutron stars. One such event in 2017 wasn't just observed, it was heard. Gravitational wave detectors felt the ripples first, triggering telescopes worldwide to document the accompanying light show, a kilonova where heavy elements like gold and platinum were forged in the cosmic fire. But it's not just about speed, it's about coverage. Projects like the Zwicky Transient Facility scan the entire visible sky every 2 nights, flagging anything that changes, stars that flicker, asteroids that streak, supernova that flare. The data deluge is overwhelming, which is where citizen scientists step in. Platforms like Galaxies enlist volunteers to classify oddities algorithms might miss. In 2008, a Dutch schoolteacher scrolling through telescope images spotted a strange green smudge, now known as Hanny's Voorwerp, a cosmic ghost lit by a quasar's long dead beam. The most thrilling aspect, time-domain astronomy is rewriting the rules of cosmic predictability. Some phenomena, like tidal disruption, events where stars are shredded by black holes, were once thought to follow predictable timelines. Now we're learning they can capriciously flare or fade, offering clues about black hole spins and stellar composition. Even familiar objects surprise us. Betelgeuse, the red giant in Orion, suddenly dimmed in 2019, sparking speculation it might go supernova. Telescopes caught every twist, revealing not an imminent explosion but a belched-out dust cloud, a stellar hiccup we'd have missed a generation ago. This isn't just about watching the sky change, it's about catching the universe in the act. Every flicker, flare, or fade tells a story about how stars die, how matter collides, how galaxies evolve. And with next-generation tools like the Vera Rubin Observatory coming online, we're about to witness the cosmos not as a gallery of still images, but as a high-definition movie, one where the plot twists arrive faster than we can predict them. Picture trying to understand a thunderstorm using only your eyes. You'd miss the rumble of distant thunder, the electric charge in the air, the way rain feels against your skin. For centuries, that's how we studied the cosmos, one sense at a time. But now, we're witnessing a revolution in how we observe the universe, and it's all thanks to multi-messenger astronomy, a discipline that doesn't just listen or look, but does both simultaneously, weaving together clues from light, gravitational waves, and ghostly neutrinos to tell the universe's story in high definition. The turning point came on August 17, 2017, when gravitational wave detectors in the United States and Europe caught the faint ripple of 2 neutron stars colliding 130 million light-years away. Within seconds, telescopes worldwide received automated alerts swiveling toward the source. What they captured was unprecedented, a kilonova, a fiery glow of heavy elements like gold and platinum forged in the cosmic wreckage. But the real magic lay in the data's harmony. Gravitational waves revealed the collision's physics, the object's masses, spins, and final moments. Light spectra decoded the explosion's chemistry, showing atoms being born in real time. Even neutrinos, though none were detected that day, could theoretically carry details about the extreme conditions inside the merger. It was like piecing together a shattered vase using every fragment's shape, texture, and fingerprints. This synergy is rewriting astrophysics. Take black holes. Observing one through light alone is like studying a tornado by the debris it throws. Add gravitational waves, and suddenly you feel the storm's vibrations. Combine both with neutrinos, and you might glimpse the tornado's hidden eye. Already, multi-messenger observations have solved long-standing puzzles. Gamma-ray bursts, once thought to come in two distinct flavors, now appear to form a spectrum linked to their merger types. The heaviest elements in the periodic table, long theorized to form in neutron star collisions, finally have a confirmed cosmic forge. But the implications run deeper than individual discoveries. Multi-messenger astronomy is exposing the limits of single-method observation. Light can be bent or obscured. Gravitational waves reveal dynamics but little about environment. Neutrinos slip through everything but rarely interact. Together, they compensate for each other's blind spots. When a supernova explodes, its neutrinos arrive hours before the light, offering early warnings. Gravitational waves from merging black holes carry details no telescope could see. And light, especially across multiple wavelengths, fills in the color and context. The future holds even bolder possibilities. Imagine detecting a supernova's gravitational waves, neutrinos, and light simultaneously, reconstructing the star's death in 3 independent data streams. Or catching a tidal disruption event where a black hole shreds a star, with all 3 messengers, revealing how matter behaves under extreme gravity. Projects like the Rubin Observatory and next-generation gravitational wave detectors are being designed with this synergy in mind, their alerts feeding real-time to a global network of instruments. What makes this approach so transformative isn't just the volume of data, it's the dialogue between them. The universe speaks in many tongues, and for the first time, we're fluent enough to listen to them all at once. Every combined observation is a Rosetta Stone, translating the cosmos's secrets into a language we can finally understand. And if history is any guide, the most thrilling chapters are yet to come. If you've ever tried to focus a pair of binoculars, you know the sharper the image, the clearer the details become. Now, imagine doing that with telescopes separated not by inches, but by millions of miles. That's the revolutionary power of space-based interferometry, a technique that combines distant observatories into a single planet-sized eye peering into the cosmos. Unlike traditional telescopes limited by the size of their mirrors, interferometers leverage the void between spacecraft to achieve resolution so sharp they could spot a coin on the moon's surface from Earth. The principle is deceptively simple. When 2 telescopes observe the same object from different vantage points, the light waves they collect arrive slightly out of sync. By meticulously measuring these tiny offsets, a process called interferometry, we can reconstruct details far beyond what either telescope could see alone. On Earth, arrays like the Event Horizon Telescope famously used this method to capture the first image of a black hole's shadow. But space is where interferometry truly shines. Without atmospheric distortion or the physical limits of a single mirror, the potential is staggering. Enter LISA, the Laser Interferometer Space Antenna. Slated for launch in the 2030s, this ambitious mission will deploy 3 spacecraft in a triangular formation, trailing Earth in orbit around the Sun. Each arm of the triangle will span 2.5 million kilometers, about 6 times the distance to the Moon, connected by lasers precise enough to detect gravitational waves with wavelengths longer than entire star systems. Where ground-based detectors like LIGO catch the high-frequency chirps of stellar mass black holes colliding, LISA will tune into the universe's low-frequency hum. The mergers of supermassive black holes, the orbits of binary white dwarfs, even echoes from the Big Bang itself. But resolution isn't just about seeing farther. It's about seeing differently. Take black holes. With traditional telescopes, their event horizons appear as tiny, unresolved dots. An interferometer like LISA could map the space-time whirlpool around them, revealing how they warp their surroundings in real time. It might even spot the zoom lens effect, where a black hole's gravity bends light from objects behind it into glowing rings. And then there's dark matter. By tracking how gravitational waves distort as they pass through invisible halos, LISA could trace its distribution across galaxies, turning whispers in spacetime into a dark matter census. The future gets even wilder. Concepts like the Very Long Baseline Interferometry mission propose flinging telescopes across the solar system, using the gravitational lensing of the Sun itself to magnify distant exoplanets or peer into the hearts of quasars. Picture this: a telescope near Jupiter, another near Saturn. Their signals combine to resolve continents on a world orbiting Alpha Centauri. It sounds like science fiction, but the math checks out. What makes space-based interferometry so transformative isn't just the engineering, it's the philosophy. For centuries, we've assumed bigger mirrors meant better views. Now, we're realizing the cosmos's finest details hide not in the glass, but in the gaps between them. The sharpest images of the universe won't come from a single flawless lens, but from the delicate dance of light across the void, stitching together a tapestry of discovery, one laser measured wavelength at a time. The cosmic microwave background isn't just ancient light. It's a message in a bottle from the universe's infancy, a fossilized whisper of heat from when everything was smaller than a single atom. This afterglow, discovered accidentally in 1965 by radio astronomers puzzled by persistent static, turned out to be the oldest light we can see. Photons released when the universe cooled enough to become transparent, just 380,000 years after the Big Bang. Picture a blacksmith's forge cooling from white-hot to red, then fading to darkness, except this glow never entirely vanished. It stretched across the cosmos as space expanded, cooling to mere 3 degrees above absolute zero, and it's still everywhere around us. Every time your television picks up static between channels, about 1% of that snowy haze is the echo of creation itself. But the cosmic microwave background isn't just a relic, it's a Rosetta Stone. Tiny fluctuations in its temperature, variations as small as 1 part in 100,000, reveal the seeds of all cosmic structure. Denser patches became galaxies, sparser regions stretched into voids. Experiments like the Simon's Observatory, a sprawling array of ultra-sensitive telescopes in Chile's Atacama Desert, map these fluctuations with microscopic precision. Their secret weapon, polarization. As the early universe's photons scattered off electrons, they left behind a faint directional imprint, like sunlight reflecting off a pond. This polarization encodes the universe's first tremors, gravitational waves from cosmic inflation, the theorized exponential expansion that occurred a trillionth of a second after the Big Bang. Detecting these patterns would be like finding the fingerprints of whatever force kicked inflation into gear. The implications are staggering. If inflation's signature is there, it could reveal whether the force driving it was a quantum field, extra dimensions, or something entirely unforeseen. The cosmic microwave background might even hold clues about dark energy's nature. By comparing the background's large-scale patterns with how galaxies cluster today, scientists can track how dark energy's push has evolved over billions of years. It's forensic cosmology, using the afterglow's wrinkles to reconstruct the universe's entire life story. What makes this work so revolutionary isn't just the technology, it's the sheer audacity of the questions we're asking. We're not just studying stars or galaxies anymore, we're reverse engineering reality's blueprints from the faintest whisper of heat. And with next-generation experiments like SIMBI-S4, which will deploy telescopes across the South Pole and Chile. We're on the verge of reading those blueprints in higher definition than ever before. The universe left us a treasure map in its oldest light. Now we're finally learning how to follow it. Mapping the universe in 3 dimensions sounds like science fiction, but thanks to projects like the Dark Energy Survey, it's become a breathtaking reality. Imagine if every galaxy in the observable cosmos were a single dot in a colossal connect-the-dots puzzle. Now picture linking those dots not just across the flat plane of the night sky, but into the depths of space, creating a 3-dimensional atlas of everything. That's exactly what astronomers are doing, and what they're uncovering is rewriting our understanding of cosmic structure itself. The Dark Energy Survey doesn't just map galaxies, it traces the invisible scaffolding holding them together. Dark matter, that elusive substance outweighing visible matter 5 to 1, doesn't emit or absorb light, but its gravitational pull bends the path of light from distant galaxies, a phenomenon called weak gravitational lensing. By measuring these subtle distortions across millions of galaxies, the survey reveals dark matter's distribution in unprecedented detail. It's like deducing the shape of a mountain range by watching how wind bends smoke drifting past. And the results are staggering: vast cosmic webs, filaments of dark matter stretching billions of light years, with galaxies clinging to them like dew on a spider's silk. But the survey's true quarry is even stranger: dark energy, the mysterious force accelerating the universe's expansion. By combining galaxy positions with supernova distances, the survey measures how this expansion has changed over cosmic time. One technique involves Baryon acoustic oscillations, ghostly ripples frozen into the universe's structure when it was just 400,000 years old. These ripples act like cosmic yardsticks. By seeing how their apparent size changes with distance, astronomers can track the universe's stretching. The latest data suggests dark energy's push has been eerily consistent, a finding that both confirms and deepens the mystery. What makes these 3D maps revolutionary isn't just their scale, it's their precision. Previous surveys charted hundreds of thousands of galaxies. The Dark Energy Survey catalogued hundreds of millions. With tools like the Vera Rubin Observatory's Legacy Survey of Space and Time set to map billions, we're entering an era where cosmic cartography isn't just descriptive, it's predictive. These maps could reveal whether dark energy's strength varies across space or time, hinting at new physics beyond Einstein's equations. They might even uncover flaws in our most cherished theories, like an explorer finding continents missing from all known maps. This isn't just astronomy, it's archaeology on a universal scale. Every galaxy plotted, every dark matter filament traced, is a clue to how the cosmos grew from a seething quantum soup to the grand structure we see today. And as these surveys grow ever more detailed, they're doing more than filling in blank spots on the map. They're showing us that the universe isn't just expanding, it's unfolding, revealing layers of complexity we're only beginning to decipher. Every time you see a rainbow, you're witnessing nature's own spectrograph at work, sunlight split into its component colors. But astronomers take this simple phenomenon to extraordinary lengths, using advanced spectroscopy to unravel the universe's deepest secrets. By dissecting starlight into exquisite detail, they can read cosmic objects like chemical fingerprints, uncovering compositions from millions of light years away. It's not magic, it's the meticulous science of decoding photons, where every subtle shift in color or intensity reveals hidden truths about the cosmos. Take something as fundamental as a star's composition. When starlight passes through a high-resolution spectrograph, dark lines appear at specific wavelengths like barcodes missing certain colors. These absorption lines correspond to elements in the star's atmosphere: hydrogen, helium, calcium, even traces of gold. Each element leaves its unique signature, allowing astronomers to reconstruct stellar chemistry with astonishing precision. In 2019, the Espresso instrument at Chile's Very Large Telescope detected lithium in an ancient star, a clue about nucleosynthesis just minutes after the Big Bang. Other spectrographs have spotted stars with bizarrely high oxygen or carbon content, hinting at violent pasts where they cannibalized neighboring planets. But spectroscopy does far more than catalog elements. The same dark lines act as cosmic speedometers. When a star moves toward us, its light waves get compressed, shifting the lines toward blue. When it recedes, they stretch toward red, the famous Doppler effect. This is how we measure galactic rotations, detect the tug of unseen planets, and even track the universe's expansion. The HARP spectrograph, for instance, clocks star movements with meter-per-second precision, sensitive enough to spot Earth-sized worlds by their gravitational wobbles. One recent study used these minute shifts to confirm Proxima Centauri b, an exoplanet in its star's habitable zone just 4 light-years away. The real frontier, though, lies in exoplanet atmospheres. When a planet transits its star, some starlight filters through its gaseous envelope, imprinting atmospheric molecule signatures on the spectrum. The James Webb Space Telescope's NIR-SPEC instrument has turned this into an art form, identifying water vapor, carbon dioxide, and even potential biosignatures like dimethyl sulfide in alien skies. In 2023, researchers analyzing Webb data reported detecting methane and carbon dioxide on K218b, a Hycean world with a possible water ocean under a hydrogen-rich atmosphere, a tantalizing hint of conditions suitable for life. Spectroscopy's power extends beyond planets and stars. Quasars billions of light-years away leave absorption lines in their light as it passes through intervening gas clouds, creating cosmic timelines of element formation. The Keck Observatory's highest spectrograph has mapped these forests of lines to track how oxygen and iron became more abundant over cosmic time. Even the diffuse gas between galaxies, nearly invisible to telescopes, betrays its presence through faint spectral fingerprints. What makes this technology so transformative is its universality. The same principles that identified sodium in the Sun's atmosphere in 1859 now probe atmospheres of worlds orbiting distant stars. Every photon reaching Earth carries encoded information about its journey, the temperatures it passed through, the elements it encountered, even the gravitational fields it traversed. Spectroscopy doesn't just show us the universe, it lets us taste its chemistry, measure its pulse, and read its history written in light. And as instruments grow ever more sensitive, we're not just decoding the cosmos anymore, we're learning its language. The universe has always been humanity's shared frontier, but for centuries, exploring it required access to elite institutions or expensive equipment. That era is over. Today, some of cosmology's most exciting breakthroughs aren't happening in ivory towers or atop remote mountains. They're unfolding on home computers and smartphones, powered by millions of curious minds eager to assist in discovery. This is the age of citizen science, where amateur stargazers and professional astronomers collaborate as equals, sifting through celestial data too vast for any single team to tackle alone. Take Galaxies Zoo, the project that rewrote the rules of who gets to do science. Launched in 2007, it invited volunteers to classify galaxies from telescope images, a task requiring human intuition to spot oddities algorithms might miss. The response was overwhelming. Within months, over 50,000 people had made more than 50 million classifications, uncovering rare galactic shapes like the emerald green Voorwerp, a quasar-lit gas cloud spotted by a Dutch schoolteacher. What began as a crowdsourcing experiment became a revolution, proving that public enthusiasm could accelerate research at unprecedented scales. Now, Galaxy Zoo's descendants let anyone hunt for supernova, track asteroid rotations, or even search for Planet 9 in archival images, all from their living rooms. The beauty of these projects lies in their serendipity. Professionals design the tools, but amateurs often make the wildcard finds. In 2016, a retired radio engineer named Hanny van Arkel, combing through Galaxy Zoo data, noticed a strange smudge near a spiral galaxy. Astronomers initially dismissed it as an artifact until follow-up observations revealed it was a never-before-seen phenomenon. A light echo from a quasar that had flickered off millennia ago, its final photons still illuminating interstellar gas. Dubbed Hani's Vorwerp, it became a Rosetta Stone for understanding how quasars shape their surroundings. Similar stories abound. Amateurs using NAS, a planet hunters platform, identified dozens of exoplanet candidates overlooked by algorithms, including a rare circumbinary world orbiting 2 stars. But the impact goes beyond individual discoveries. Citizen science is democratizing the scientific process itself. Platforms like Zooniverse offer training modules that turn casual participants into skilled classifiers, while projects like Backyard Worlds tap into humanity's innate pattern recognition, a skill even advanced AI struggles to match. When the Hubble Space Telescope needed help identifying debris from asteroid collisions, volunteers mapped thousands of dust trails in weeks. When the TESS satellite's flood of exoplanet data overwhelmed researchers, amateur astronomers confirmed candidates using backyard telescopes. The line between scientist and enthusiast is blurring, and the universe is richer for it. What makes this collaboration so transformative isn't just the extra pairs of eyes, it's the diversity of perspectives. A professional might focus on known variables, while a newcomer spots anomalies precisely because they don't know what to expect. It's no coincidence that citizen scientists often find the outliers, supermassive black holes where they shouldn't be, stars behaving erratically, or galaxies defying classification. Their fresh eyes see the cosmic forest and the trees. This isn't just about outsourcing labor. It's about rewriting the social contract of discovery. When the Vera Rubin Observatory begins its decade-long survey next year, it will generate 10 million alerts nightly. No research team could possibly vet that deluge alone, but a global army of volunteers, they'll comb through it, flagging the flashes and flickers that might herald new physics. The universe's next great revelation could come from a teenager in Mumbai, a teacher in Rio, or a retiree in Oslo. Because in this new era of exploration, the cosmos isn't just for those with PhDs, it's for anyone who dares to look up and wonder. Quantum entanglement, the phenomenon Einstein famously called spooky action at a distance, has long been confined to physics labs where particles linked across space defy classical intuition. But what if this quantum weirdness could be harnessed to peer deeper into the cosmos than ever before? Astronomers are now exploring how entangled particles could become the ultimate telescopic upgrade, pushing resolution beyond the limits of light itself. Here's how it works. In traditional telescopes, resolution depends on aperture size. The larger the mirror, the finer the details it can discern. But entangled photons operate under different rules. When 2 particles are entangled, measuring one instantly affects its partner, no matter how far apart they are. By exploiting this link, scientists are developing quantum telescopes that could, in theory, achieve resolutions equivalent to a mirror the size of a planet. Imagine capturing the surface features of an exoplanet light years away, or spotting moon-sized structures near a black hole's event horizon. One groundbreaking experiment in this field involves quantum imaging. Researchers at the University of Glasgow recently demonstrated how entangled photon pairs could be used to detect objects with less light than classical methods require. Their setup used one photon to interact with a sample while its entangled twin carried information to a detector, effectively creating an image without the probe photon ever directly touching the object. Applied to astronomy, this technique could let us study faint cosmic objects without drowning their signals in noise, like listening to a whisper across a crowded room by tuning into its echo in a silent chamber. But entanglement's potential doesn't stop at sharper images. It might also help us test the very fabric of spacetime. Theories suggest that spacetime itself could have a quantum structure, a foamy, granular texture at microscopic scales. If so, entangled particles sent across astronomical distances might decohere, their quantum link disrupted by subtle spacetime fluctuations. Proposed missions like Space Quest aim to beam entangled photons from space to Earth, probing whether the universe's underlying geometry leaves fingerprints on quantum connections. It's like using entanglement as cosmic sandpaper, feeling for imperfections in reality's surface. The implications are staggering. Quantum astronomy could reveal celestial details hidden since the dawn of telescopic observation, while simultaneously answering existential questions about spacetime's nature. We're not just building better telescopes anymore, we're redefining what observation means. And as quantum technology matures, the line between the infinitesimally small and the astronomically vast may blur entirely, revealing a universe far stranger and far more connected than we ever imagined. While our most powerful telescopes peer billions of light years into the cosmic deep, some of the universe's most astonishing revelations are unfolding right in our planetary neighborhood, thanks to intrepid robotic explorers. Mars rovers like Perseverance don't just traverse the red planet's dusty plains. They function as extraterrestrial geologists, bristling with instruments that drill, analyze, and even cache samples for future return to Earth. Every scratch mark left by its wheels could rewrite our understanding of whether life ever took root beyond our world. Take the Jezero crater, Perseverance's landing site. Orbital data suggested it once held a vast lake, but the rover's ground truth observations revealed sedimentary layers bearing telltale signs of ancient river deltas, precisely the kind of environment where microbial life might have thrived billions of years ago. Then there's the audacious Europa Clipper, NASA's upcoming mission to Jupiter's icy moon. Unlike Mars, Europa hides its secrets beneath a global ocean encased in a shell of ice up to 15 miles thick. Yet this frozen world may harbor more liquid water than all of Earth's oceans combined. The Clipper won't land. Instead, it will perform dozens of low-altitude flybys, using ice-penetrating radar to map the subsurface sea while spectrometers sniff faint plumes erupting through the ice. These geysers, first spotted by the Hubble Space Telescope, could offer free samples of Europa's hidden ocean, no drilling required. Imagine analyzing alien seawater for amino acids or other organic molecules without ever breaking through the ice. What makes these missions revolutionary isn't just their technology, it's their strategy of exploring not just surfaces but histories. The Mars Sample Return Campaign, a multi-mission effort involving Perseverance, aims to bring back tubes of Martian soil by the 2030s. Those samples could settle debates about Mars's wet past and its potential for ancient life with laboratory precision no rover can match. Similarly, ESA's JUICE mission will study Jupiter's moons Ganymede and Callisto alongside Europa, comparing their subterranean oceans to understand why some icy worlds remain geologically active while others freeze solid. Yet the surprises keep coming. The Dragonfly rotorcraft, slated to reach Saturn's moon Titan in the 2030s, will hop across dunes of hydrocarbon sand under a smoggy orange sky, a drone exploring a world where methane flows like water. Even Venus, long dismissed as a hellish wasteland, is back on the exploration agenda after the shock discovery of potential phosphine gas in its clouds, a possible biosignature that inspired NASA Veritas and Da Vinci missions. These probes remind us that the solar system isn't some static museum exhibit, it's a dynamic, evolving frontier. Every new landing, every sample collected, peels back another layer of our cosmic backyard's untold stories. And as these mechanical pioneers push further toward the methane seas of Titan, the geysers of Enceladus, or the metallic core of Psyche, they're proving that you don't need to travel across the galaxy to find the extraordinary. Sometimes the universe's best-kept secrets are hiding in plain sight. Deep beneath Antarctica's ice sheets, in scalding volcanic vents at the ocean floor, and even inside rocks buried miles underground, life persists in conditions that would be lethal to nearly every other organism on Earth. These are extremophiles microbes that don't just survive in environments we once thought uninhabitable, they thrive there. Their existence has rewritten biology's rulebook, proving life can adapt to crushing pressures, blistering acidity, and even the vacuum of space. And if life can flourish in Earth's most hostile corners, why not on Mars's frozen plains, in Europa's subsurface ocean, or on an exoplanet orbiting a red dwarf star? Astrobiologists are now using these tenacious organisms as blueprints for where and how to hunt for life beyond our planet. Take Deinococcus radiodurans, a bacterium that shrugs off radiation doses thousands of times stronger than what would kill a human. It repairs its shattered DNA with astonishing efficiency, surviving in nuclear waste facilities and even the vacuum of space during experiments on the International Space Station. Then there's Psychromonas ingrahamii, found thriving in Arctic sea ice at temperatures as low as -20 degrees Celsius. These organisms don't merely endure extreme conditions, they've evolved to depend on them, reshaping our understanding of life's potential habitats. This revelation has direct implications for the search for extraterrestrial life. Jupiter's moon Europa, with its subsurface ocean heated by tidal forces, might host hydrothermal vents similar to those on Earth where extremophiles flourish without sunlight. NASA Europa Clipper mission will analyze plume material for organic compounds, while future landers could drill through the ice to search for microbial communities like those in Antarctica's Lake Vostok. Similarly, Mars's recurring slope-linear dark streaks that may indicate seasonal brine flows could be oases for halophiles, salt-loving microbes analogous to those in Chile's Atacama Desert or the Dead Sea. But the real game-changer is how extremophiles hint at life's universality. Amino acids, the building blocks of proteins, have been found in meteorites like Murchison, which crashed in Australia in 1969. Comets like 67P Churyumov-Gerasimenko, studied by the Rosetta mission, contain glycine and phosphorus, key ingredients for life. If these compounds form readily in space and life can adapt to such diverse environments, the galaxy might be far more hospitable than we thought. Astrobiologists are now designing experiments to test these ideas. On the International Space Station, the Expose-R2 mission exposed extremophiles to open space for 18 months. And some survived, protected only by a thin layer of artificial meteorite. Meanwhile, labs are simulating conditions on Saturn's moon Titan, where methane lakes might host life with a completely different biochemistry than Earth. The lesson from extremophiles is clear: life is neither fragile nor rare. It's stubborn, creative, and endlessly adaptable. As we search the cosmos, we're no longer asking if life exists elsewhere, we're asking where it's hiding and how radically different it might be from anything we've seen before. The universe's harshest corners might just be its most fertile ground for life's next great surprises. Wormholes, those fantastical cosmic shortcuts piercing through space-time, have long been the stuff of science fiction. But what if they aren't just plot devices for interstellar travel, but real structures hiding in plain sight? Theoretical physics tells us these tunnels through the universe's fabric could exist, warping space so drastically that distant points touch. Einstein's equations allowed for them, yet detecting one seemed impossible until now. Cutting-edge tools are turning this mathematical curiosity into a searchable reality, probing the cosmos for spacetime's most elusive wrinkles. The challenge lies in wormholes' very nature. Unlike black holes, which announce themselves with gravitational roars and glowing accretion disks, a stable wormhole might leave almost no trace. No light would escape it, and its entrance could mimic a black hole's silhouette perfectly. So how do you find something designed to be invisible? The answer might lie in its gravitational shadow. Recent studies suggest that a wormhole's throat, the tunnel connecting its two mouths, could subtly distort the light from stars behind it in ways a black hole wouldn't. Telescopes like the Event Horizon Telescope, which captured the first black hole image, might soon scan for these telltale warps. Picture spotting a faint lensing pattern where space-time pinches into a tunnel rather than a dead-end singularity. But wormholes pose another puzzle. They'd need exotic matter to stay open. Unlike normal matter, this hypothetical substance would have negative energy, propping the tunnel open against gravity's crushing force. Here's where dark energy, the mysterious force accelerating the universe's expansion, enters the story. Some theories suggest dark energy could manifest properties akin to exotic matter. If so, mapping its distribution with projects like the Dark Energy Survey might indirectly reveal regions where wormholes could thrive. It's like tracing the scent of something invisible, finding the shadow of a shadow. The boldest experiments are testing these ideas beyond theory. Quantum labs are attempting to create microscopic wormhole analogs using entangled particles, where information seems to tunnel between them instantaneously. While not true space-time bridges, these experiments could reveal physics that makes cosmic-scale wormholes plausible. Meanwhile, astronomers are scouring gamma-ray bursts for anomalies, unexpected echoes, or energy patterns that might hint at a wormhole's presence. One tantalizing proposal suggests that certain ringing frequencies in gravitational wave data could betray a wormhole's resonant vibrations, like tapping a wine glass to hear its hidden flaws. The implications stagger the imagination. Confirming a wormhole wouldn't just revolutionize physics, it would rewrite humanity's place in the cosmos. Suddenly, the galaxy's farthest reaches might be a single step away. But here's the twist: even if we never find one, the search itself is stretching our understanding of reality. Every null result forces us to refine our theories, pushing the boundaries of what's possible. Whether wormholes exist or not, the hunt for them is proving that the universe's wildest possibilities are worth chasing, not as fantasies, but as testable truths waiting to be uncovered. Supercomputers are the silent architects of cosmic understanding, crunching numbers at scales that would melt ordinary processors into slag. These digital titans don't just calculate, they dream, constructing virtual universes so detailed they blur the line between simulation and reality. Take the Millennium Simulation, a landmark project that traced the evolution of 10 billion particles across 13 billion years of cosmic history. Inside its code, dark matter coalesced into filaments, galaxies spun into existence, and black holes merged in silent fireworks, all before breakfast in the real world. This wasn't just a pretty animation, it was a stress test for our theories, revealing how tiny quantum fluctuations in the early universe snowballed into the cosmic web we see today. But simulating a universe isn't like rendering a movie. Every particle interacts with every other particle, creating a computational nightmare where the workload scales exponentially. That's why machines like Frontier, the world's fastest supercomputer, are revolutionary. With its 1.1 exaflops of power, that's a quintillion calculations per second, it can model galaxy collisions with unprecedented precision, tracking billions of stars in a dance dictated by gravity's invisible hand. These simulations aren't just academic exercises. When LIGO detects gravitational waves, supercomputers reconstruct the events in silico, comparing ripples in spacetime to libraries of simulated mergers. It's like replaying a crime scene to identify the weapon, except the weapon might be two black holes spinning at half the speed of light. The boldest simulations venture into territory beyond observation, like the multiverse. Using string theory's mathematical scaffolding, projects like the Calabi-Yau manifold project simulate how extra dimensions curled into shapes smaller than atoms might influence physics in alternate realities. These aren't sci-fi fantasies, they're hypotheses rendered in code, probing whether our universe's constants, like the strength of gravity, are mere accidents or inevitable outcomes of deeper laws. One tantalizing result: certain simulated universes with slightly weaker nuclear forces never form carbon, suggesting life as we know it might depend on a razor-thin balance of cosmic parameters. What makes these digital cosmos so transformative is their predictive power. Before JWST spotted those unexpectedly massive early galaxies, supercomputers running modified dark matter models had already hinted they might exist. Now, as we push toward digital twin universes, simulations so precise they could forecast galaxy distributions or dark energy's evolution, we're not just observing the cosmos anymore. We're holding up a mirror to it, searching for cracks in the reflection that might reveal entirely new physics. The universe's greatest secrets may not lie in the stars, but in the silicon hearts of machines brave enough to imitate them. The James Webb Space Telescope has rewritten the cosmic rulebook, but it's merely the opening act in a revolution that's about to accelerate. Imagine a telescope so powerful it could directly image Earth like planets around nearby stars, analyzing their atmospheres for signs of life while simultaneously mapping the universe's expansion with pixel-perfect precision. That's the promise of the Habitable Worlds Observatory, NAS, a next flagship mission slated for the 2030s. Designed as a hybrid between Webb's infrared vision and Hubble's ultraviolet clarity, this observatory will carry a coronagraph so advanced it can block starlight by a factor of 10 billion, revealing faint planets hiding in the glare. Picture trying to spot a firefly next to a searchlight from 1,000 miles away, and you'll grasp the engineering triumph this represents. But the Habitable Worlds Observatory isn't alone in pushing boundaries. Europe's Pluto mission, launching in 2026, will monitor millions of stars for exoplanet transits with an array of 26 cameras, combing the cosmos for rocky worlds in habitable zones. Meanwhile, the Nancy Grace Roman Space Telescope will conduct a galactic census when it launches in 2027, its wide-field instrument surveying the sky 1,000 times faster than Hubble. Roman's key target: dark energy's influence on cosmic structure, using a technique called weak gravitational lensing to map how invisible matter warps light from distant galaxies. It's like turning the universe itself into a magnifying glass to weigh the unseeable. The real game changer might be what comes after these missions. Concept studies are already underway for telescopes that would dwarf even Webb's capabilities. The Large Ultraviolet Optical Infrared Surveyor, or LUVOIR, proposes a 15-meter segmented mirror, 3 times wider than Webb's, that could directly photograph exoplanets as small as Mars. Then there's the Origin Space Telescope, a far-infrared observatory so sensitive it could trace water's journey from interstellar clouds to planetary surfaces, unveiling the cosmic recipe for habitable worlds. These aren't just incremental upgrades, they're leaps into realms of observation we've only theorized about. What makes this era unprecedented isn't just the technology, it's the convergence. For the first time, gravitational wave detectors, neutrino observatories, and multi-wavelength telescopes will operate in concert, creating a symphony of cosmic insight. A single exoplanet discovery might combine data from Webb's atmospheric spectra, Roman's precise orbit measurements, and future interferometers mapping surface features. We're moving beyond snapshots of the universe to high-definition, multi-sensory immersion where every wavelength, every particle, every ripple in space-time contributes to the story. The golden age of astronomy isn't some distant future. It's unfolding right now, with each new mission peeling back another layer of cosmic mystery. And if history is any guide, the most profound revelations won't be the ones we're anticipating, but the ones we can't yet imagine. The universe has kept its deepest secrets hidden for billions of years. Now, finally, we're building the tools to uncover them. For over 60 years, humanity has cast electronic nets into the cosmic ocean, listening for whispers of intelligence beyond our world. The search for extraterrestrial intelligence, SETI, has evolved from single-dish radio telescopes to a globe-spanning network of antennas, supercomputers, and even smartphone apps, all sifting through the static of the universe for that elusive needle in the haystack, a signal that says you're not alone. Projects like Breakthrough Listen represent the cutting edge of this quest, scanning millions of stars across 10 times more radio spectrum than all previous SETI efforts combined. But this isn't your grandparents' alien hunt anymore. The game has changed not just in scale but in strategy. Take Breakthrough Listen's approach. Instead of focusing solely on the water hole, a quiet band of radio frequencies between hydrogen and hydroxyl emissions where scientists once theorized aliens might broadcast, this project casts a far wider net. Its telescopes, including the Mammoth Green Bank dish in West Virginia and the Parkes Observatory in Australia, now scan from 1 GHz up to 10, hunting for both deliberate signals and accidental technosignatures. Imagine tuning an AM radio through every station on the dial, but doing it for every star within 100 parsecs. That's the scope of modern SETI. Even more revolutionary is how artificial intelligence pores over this data. Machine learning algorithms trained on terrestrial interference cell towers, satellite bursts, even microwave ovens, can filter out earthly noise to spotlight anomalies that defy natural explanation. In 2020, one such anomaly, dubbed BLC1, briefly set pulses racing before being traced to human-made interference, proving these systems can spot needles even when they turn out to be rusted nails. Yet radio waves are just the beginning. Optical SETI now searches for laser pulses that could outshine a star for nanoseconds and interstellar Morse code. The Veritas telescope array in Arizona scans the skies for these flashes, while the Panoply project builds dedicated optical observatories to catch them. There's even a push to hunt for physical artifacts, from Dyson spheres harvesting starlight to atmospheric pollutants betraying industrial civilizations. The key insight: alien technology might leave footprints far stranger than a radio broadcast. Consider Tabby's star, whose erratic dimming sparked theories of a megastructure before dust clouds offered a likelier explanation. The lesson wasn't that aliens built a Dyson swarm, but that cosmic oddities can guide us toward new search parameters. The boldest shift, though, is in who gets to participate. SETI at home once harnessed millions of personal computers to analyze data during screensaver downtime. Now, platforms like Zooniverse's SETI Live let anyone scan telescope data for unusual patterns. Even the Allen Telescope Array, built specifically for SETI, shares its observations in near real time, turning the search into a global collaboration. This democratization reflects a deeper truth. Decoding the universe's greatest riddle shouldn't belong to elites in lab coats. It's a human endeavor, powered by curiosity that spans continents and generations. So are we on the verge of contact. Statistically, the cosmos feels too vast for silence. With trillions of planets, even vanishingly slim odds suggest someone's out there. Yet the great filter looms, the unsettling idea that civilizations might inevitably snuff themselves out before making contact. SETI true value may lie not in finding aliens, but in realizing how rare or how resilient intelligence might be. Every silent frequency is a clue, every null result a puzzle piece. And if that long-awaited signal ever comes, the protocols are ready, the world's telescopes will pivot, and humanity will face a moment unlike any in history. Until then, we keep listening, not just for them, but for what the search teaches us about our own place in the dark. 20-second cosmic blips, fast radio bursts, flash across the universe with the energy of 500 suns, and then vanish without a trace. These millisecond flares, first discovered in 2007, defy easy explanation. One moment, a radio telescope picks up a spike of energy brighter than entire galaxies, the next silence. Their randomness makes them maddeningly hard to study, like trying to solve a puzzle where the pieces keep disappearing. Yet these fleeting signals might hold clues to some of the cosmos' most violent events, or even entirely new physics we've yet to imagine. The leading suspect, magnetars, neutron stars with magnetic fields so strong they could erase a credit card from halfway to the moon. In 2020, astronomers caught one red-handed. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, linked a fast radio burst to a magnetar in our own galaxy. As the star's crust quaked under magnetic strain, it likely unleashed a wave of particles that twisted into radio brilliance. But here's the twist: not all bursts fit this mold. Some repeat at erratic intervals, others arrive solo, and a few pulse with patterns so precise they resemble cosmic lighthouses. If magnetars explain some bursts, what's creating the rest? Enter the wilder theories. Colliding neutron stars might generate bursts as their crushing gravity ripples space-time. Or perhaps superconducting cosmic strings hypothetical defects in the universe's fabric snap and release energy as they vibrate. Some have even speculated carefully about advanced civilizations beaming power across galaxies, though natural explanations remain far more likely. The truth is messy, and that's what makes these bursts so thrilling. Every new detection scrambles the puzzle anew. What's changing the game is our ability to trace them. Earlier bursts were localized to broad swaths of sky, leaving astronomers to sift through thousands of galaxies for the source. Now, networks like the Deep Synoptic Array in California can pinpoint a burst's origin within seconds, sometimes to a single distant galaxy. This precision matters because the burst's journeys across space leave fingerprints. As the signals traverse intergalactic plasma, they slow slightly, revealing how much invisible matter they've passed through. It's like cosmic sonar, mapping the universe's hidden scaffolding one burst at a time. The deeper we look, the stranger it gets. Some bursts arrive with a sad trombone effect, their frequencies sliding downward as if the universe itself were playing a prank. Others come in pairs or with afterglows in other wavelengths. The Australian Square Kilometre Array Pathfinder recently detected one burst from a galaxy so far away its light took 8 billion years to reach us, a message from when the universe was barely half its current age. Whatever's causing these bursts, it's been happening for eons, hidden in plain sight until our technology caught up. Fast radio bursts remind us that the cosmos thrives on mystery. Just when we think we've got a handle on things, the universe tosses out a curveball, a flicker of radio noise that rewrites the questions we thought to ask. And that's the beauty of it. Every unexplained flash isn't just a problem to solve. It's an invitation to look deeper, think wilder, and remember that the universe's greatest surprises often come in the briefest moments. Dark energy is the universe's most confounding riddle. An invisible force not just expanding the cosmos but doing so at an ever-increasing pace. Picture blowing up a balloon that inflates faster the bigger it gets, defying every expectation of how gravity should behave. This isn't just a curiosity, it's a fundamental challenge to our understanding of reality. For decades, we've known the universe is growing, but the discovery in the late 1990s that this expansion is accelerating sent shockwaves through cosmology. Suddenly, we faced a glaring gap in our knowledge. 70% of the universe's energy budget seems to be this mysterious dark energy, and we have no idea what it actually is. The leading candidate, Einstein's cosmological constant, a subtle energy woven into the fabric of space itself. It's an elegant idea. Empty space isn't truly empty but seething with quantum fluctuations that push everything apart. The problem, when physicists calculate how strong this energy should be, the theoretical value overshoots observations by a factor of 10 to the power of 120. That's like predicting an ocean's depth should be the distance to the moon, a discrepancy so vast it suggests we're missing something profound. That's where next-generation experiments come in. The Dark Energy Spectroscopic Instrument, or DESI, is mapping millions of galaxies in 3 dimensions, tracing how their distribution has stretched over cosmic time. By measuring baryon acoustic oscillations, frozen ripples from the early universe, DESI acts like a cosmic speedometer, tracking how dark energy's push has changed across eons. Meanwhile, the European Space Agency's Euclid mission takes a different approach, scanning billions of galaxies for distortions caused by dark energy warping spacetime. Think of it as holding up a funhouse mirror to the cosmos. The more warped the reflection, the stronger dark energy's grip. But the real game changer might lie in entirely new physics. Some theories suggest dark energy isn't constant at all but evolves, growing stronger or weaker over time. Others propose it's tied to an undiscovered field permeating space, like the Higgs field but with repulsive gravity. The most radical idea, that Einstein's theory of gravity itself needs revising at cosmic scales, and what we call dark energy is just a symptom of our incomplete understanding. Projects like the Vera Rubin Observatory will test these theories by spotting anomalies in supernova brightness or galaxy motions that defy expectations. One thing's certain, solving this mystery will rewrite our cosmic destiny. If dark energy strengthens, it could tear apart galaxies, then atoms in a big rip. If it weakens, gravity might regain control, collapsing the universe in a big crunch. Or perhaps it's just the first hint of a deeper layer of reality waiting to be uncovered. Every observation, every simulation brings us closer to an answer, not just about what dark energy is, but what the universe itself is made of. The clock is ticking and the cosmos isn't waiting. Our task to listen, measure, and decode before the next great cosmic revelation slips through our fingers. Imagine if black holes weren't just the monstrous behemoths we've detected merging across the cosmos. What if they also came in miniature, relics so small and ancient they've slipped through our observational nets for billions of years? These hypothetical primordial black holes, some no heavier than a mountain yet denser than a star, could be the universe's earliest survivors, forged in the chaos of the Big Bang itself. Unlike their stellar mass counterparts born from collapsing stars, these tiny titans might have formed when extreme density fluctuations in the infant universe collapsed directly into black holes, bypassing the star stage entirely. If they exist, they'd be cosmic fossils, carrying clues about conditions in the first fraction of a second after creation, a time far older than the cosmic microwave background itself. The hunt for these elusive objects hinges on one of Einstein's most startling predictions, gravitational microlensing. When a massive object like a black hole passes between us and a distant star, its gravity bends and amplifies the star's light like a cosmic magnifying glass. For stellar mass black holes, this creates weeks-long brightening events, but a primordial black hole, its lensing effect might last mere hours or even minutes, a fleeting cosmic wink easily missed without constant sky-wide monitoring. Projects like the Optical Gravitational Lensing Experiment, or OGLE, have spent decades scanning millions of stars for such blips. In 2011, they spotted a mysterious event where a star brightened and faded in just 8 hours, too brief for a star or planet, but perfect for a lunar mass black hole drifting silently through the galactic halo. Yet microlensing isn't the only tool in play. Primordial black holes might betray their presence through more violent means. If one collided with a neutron star, it could consume the star's dense material from within, sparking X-ray flares detectable across galaxies. Others could accumulate in the cores of stars or planets, their slow consumption of matter generating subtle heat signatures, the most tantalizing possibility. These black holes might collectively make up dark matter itself, While current constraints rule out primordial black holes as the sole dark matter candidate, a population with varied masses, some as light as asteroids, others as heavy as moons, could still contribute to the invisible scaffolding shaping our universe. The implications of discovering even one primordial black hole would be profound. It would prove the young universe hosted extreme density variations beyond what inflation theory predicts. Their evaporation via Hawking radiation might even explain mysterious cosmic gamma-ray flashes. For now, they remain phantoms caught between theory and observation. But with next-generation surveys like the Vera Rubin Observatory set to scan the entire visible sky every few nights, the odds of spotting these cosmic ghosts are improving. The universe's oldest black holes might not hide much longer, and if we find them, they'll whisper secrets from a time before time when the cosmos was just taking its first breath. What if the universe we see with its galaxies, stars, and planets is just one page in an infinite cosmic library? The multiverse hypothesis, once relegated to philosophy and science fiction, is now a serious topic in physics, fueled by baffling anomalies in the cosmic microwave background and strange behavior in quantum experiments. At the heart of this idea lies inflation theory, which suggests our universe expanded exponentially in its first moments. But some models propose this expansion didn't just happen once, it could be ongoing, birthing countless bubble universes with their own laws of physics. The cosmic microwave background, that ancient afterglow from the Big Bang, holds tantalizing hints. Certain large-scale anomalies, like unexpected cold spots and asymmetrical patterns, defy standard cosmological explanations. One theory, these could be bruises from collisions with other universes in the multiverse's foam. Imagine two soap bubbles gently bumping in a sink. The slight deformation where they touch might leave a mark. The Planck satellite's detailed maps of the CMB revealed several such oddities, though skepticism remains. After all, the universe is under no obligation to conform to our expectations, but if these anomalies persist, they might be our first glimpse beyond the cosmic horizon. Meanwhile, quantum mechanics adds another layer of intrigue. In the famous double-slit experiment, particles act as if they pass through both slits simultaneously until observed when they choose a single path. The many worlds interpretation takes this further, proposing that every quantum decision spawns parallel universes. In one reality, the particle goes left, in another, right. While this idea can't be directly tested yet, experiments with entangled particles and quantum superposition push the boundaries of what reality might encompass. Critics argue the multiverse is untestable by definition. If other universes are forever beyond our reach, how can we prove they exist? But supporters counter that their influence might still be detectable. Just as shadows hint at objects outside our line of sight, anomalies in our universe's structure or constants could point to a broader cosmic landscape. The debate isn't just academic. If true, the multiverse could explain why our universe seems so finely tuned for life. With infinite variations, some would inevitably have the right conditions, no divine fine-tuning required. The implications are dizzying. A multiverse could host realities where time flows backward, gravity repels, or life takes forms beyond our imagination. Or it might be a barren statistical desert with habitable universes vanishingly rare. For now, the multiverse remains at the edge of science, too compelling to ignore, too elusive to confirm. But as we push deeper into quantum realms and map the cosmos with ever greater precision, we might uncover clues that reality is far stranger and far grander than we ever dreamed. As humanity reaches further into the cosmos than ever before, we're encountering a profound truth. Every new discovery comes with weighty responsibilities we can't ignore. Planetary protection isn't just bureaucratic red tape. It's a moral framework ensuring we don't recklessly contaminate other worlds with earthly microbes or vice versa. When NASA Perseverance rover drilled into Martian soil, its tools were meticulously sterilized not because we fear alien life, but because we respect its potential existence enough not to drown it in our biological noise. The same precautions guide missions to Europa's subsurface ocean or Enceladus geysers. These aren't merely scientific protocols, they're the first pages of an interstellar golden rule. Explore as you'd wish others to explore your own world. The stakes escalate when we consider intelligent life. The search for extraterrestrial intelligence maintains strict post-detection protocols, but how prepared are we really for that moment? In 2010, scientists debated whether to respond to a signal from Gliese 581d, not because one was received, but to stress test our collective readiness. The challenges are thorny. Who speaks for Earth? What if decoding an alien message triggers social upheaval? History offers sobering parallels. When Galileo's telescope shattered the Earth-centered cosmos, it didn't just change textbooks, it upended power structures and worldviews. A confirmed alien signal might do the same, forcing us to confront cosmic isolation or worse, cosmic neighbors with motives we can't fathom. Then there's the economic calculus of space. Asteroid mining promises rare metals, but at what cost to celestial heritage? The Moon's far side offers radio silence perfect for astronomy, until commercialization clutters the spectrum. Even starshades blocking exoplanet glare could become orbital advertising real estate. These aren't distant hypotheticals. Luxembourg already recognizes space resource ownership, while the Artemis Accords scramble to set lunar precedents. The frontier mentality that fueled Earth's exploration now demands something subtler: stewardship of the infinite, recognizing that short-term gains might permanently alter humanity's relationship with the cosmos. Perhaps the deepest ethical layer is existential. Every revelation reshapes our self-understanding, whether learning we're not the universe's center or discovering life's building blocks are universal. Finding even microbial life would force theology, philosophy, and politics to adapt overnight. The Hubble Deep Field image, revealing thousands of galaxies in a patch of sky no bigger than a grain of sand held at arm's length, already quietly shattered human exceptionalism. Future breakthroughs, a second Genesis on Europa, artifacts around Proxima Centauri, would amplify this humility exponentially. This isn't about putting brakes on discovery, it's about steering wisely. The same curiosity propelling us outward must turn inward too, asking not just can we, but should we? Because the universe isn't just a frontier to conquer, it's a mirror showing us who we are and who we aspire to become in the grand cosmic story we're only beginning to read. For centuries, space exploration was the exclusive domain of national agencies, the playground of NASA, Roscosmos, and a handful of superpowers with bottomless budgets. But something revolutionary has happened over the past 2 decades. The stars have gone corporate. Companies like SpaceX, Blue Origin, and Rocket Lab aren't just contractors building someone else's rockets. They've become the driving force behind a new era of accessibility, where reaching orbit no longer requires the backing of a government checkbook. SpaceX's Falcon 9 rockets have rewritten the economics of spaceflight. Before their reusable boosters began landing themselves on drone ships, launching a single kilogram into orbit cost around $20,000. Today, that price has plummeted by more than 80%. This isn't just about cost cutting, it's about frequency. When launches become routine, astronomers can deploy telescopes faster, planetary scientists can send more probes, and experiments that once waited decades for a ride suddenly find open seats. Consider the Transiting Exoplanet Survey Satellite, or TESS, which hitched a ride on a Falcon 9 in 2018. Its mission to scan nearby stars for planets benefited not just from SpaceX's affordability, but from its reliability. A launch window that might have taken years to secure under old models became just another Tuesday at Cape Canaveral. Then there's Blue Origin's quieter but equally pivotal role. While their New Shepard suborbital vehicle grabs headlines for celebrity joyrides, its real value lies in the microgravity experiments it hosts. Researchers studying everything from protein crystallization to fluid dynamics can now book test flights like lab time, turning what was once a rare privilege into an on-demand service. The company's orbital-class New Glenn rocket, when operational, promises to further democratize heavy payloads, potentially slashing the cost of deploying next-generation space telescopes. But the private sector's influence goes beyond rockets. Companies like L3Harris and Maxar Technologies build cutting-edge satellite buses that universities and small nations can customize, putting Earth observation and deep space communication within reach of budgets that would have been laughed out of the room in the 20th century. Even the International Space Station has transitioned from a purely government-run outpost to a mixed-use research hub, with private astronauts like Axiom Space's crews conducting experiments that range from pharmaceutical development to advanced materials testing. Perhaps the most transformative development is how these companies are tackling challenges agencies deemed too risky. SpaceX's Starship, despite its explosive test flights, represents the first credible shot at a fully reusable interplanetary spacecraft, a vessel that could carry telescopes too large for current rockets or establish lunar bases as stepping stones to Mars. Meanwhile, Rocket Lab's audacious plan to send a private mission to Venus in search of atmospheric phosphine, a potential biosignature, shows how commercial agility can pursue high-risk, high-reward science that bureaucratic timelines might sideline. This shift isn't without tension. Critics warn that a profit-driven space race could prioritize spectacle over sustainability, cluttering orbits with satellites or risking planetary protection protocols. Yet the synergy between public and private is yielding solutions even skeptics must admire. NASA's Commercial Lunar Payload Services program, for instance, taps private landers to deliver scientific instruments to the Moon, a model that splits costs while accelerating the pace of discovery. What's unfolding is nothing short of a paradigm shift. The cosmos is no longer a distant realm reserved for a select few with taxpayer funding. It's becoming a frontier where startups, universities, and even individual researchers can stake a claim, propelled by technologies and business models that treat space not as a trophy but as a workplace. The greatest legacy of these companies may not be the rockets they've built, but the doors they've kicked open, proving that the final frontier belongs to anyone bold enough to reach for it. The next decade in astrophysics promises to dissolve the boundaries between science fiction and reality, with breakthroughs poised to answer humanity's oldest questions and unravel mysteries we haven't even thought to ask yet. By 2035, we could be staring at the first definitive evidence of life beyond Earth. Missions like the Habitable Worlds Observatory will analyze exoplanet atmospheres with such precision that biosignatures, gases like oxygen, methane, or even industrial pollutants will leap from spectral data like neon signs. Picture this: a rocky world orbiting a red dwarf, its atmosphere awash in molecules that, on Earth, only exist through biological processes. The discovery wouldn't just rewrite textbooks, it would redefine our place in the cosmos, proving that life isn't a fluke but a cosmic imperative. But life isn't the only frontier. The unification of physics, Einstein's elusive dream, might finally come into focus. Gravitational wave detectors like LISA will listen for collisions between supermassive black holes, events so cataclysmic they could reveal cracks in general relativity. Meanwhile, quantum telescopes might peer into the quantum foam of spacetime itself, hunting for signs that gravity and quantum mechanics aren't opposing forces but two sides of the same coin. Imagine detecting a particle that bridges the gap or spotting a wormhole signature in gamma-ray data. These aren't just incremental steps, they're leaps toward a theory of everything, a framework stitching the cosmos together from the quantum to the cosmic scale. Closer to home, robotic explorers will turn the solar system into a bustling scientific laboratory. Europa Clipper's scans of Jupiter's icy moon could uncover plumes spewing microbial life, or at least the complex chemistry that makes life possible. On Mars, sample return missions might deliver dirt laced with fossilized microbes, their tiny forms preserved in ancient lake beds. Even Venus, long dismissed as a hellscape, could surprise us. If probes like Da Vinci confirm phosphine in its clouds, we'll face the electrifying possibility of aerial life floating above the scorching surface. Then there's dark matter, the universe's most stubborn enigma. By 2035, ultra-sensitive detectors buried deep underground or floating in space could finally snare a dark matter particle, ending the decades-long hunt. Or perhaps we'll realize it's not a particle at all, but a shadow of extra dimensions or a flaw in our gravitational equations. The answer will reshape cosmology, revealing whether the universe's hidden scaffolding is made of undiscovered matter or something far stranger. The most thrilling breakthroughs, though, might be the ones we can't yet predict. Every era of exploration has stumbled upon the unexpected black holes, dark energy, gravitational waves phenomena that defied the imagination until they didn't. As telescopes grow sharper and artificial intelligence sifts data for anomalies, we're bound to uncover cosmic oddities that rewrite the rules, perhaps a signal from an ancient civilization, a flaw in the cosmic microwave background hinting at a universe before ours, or an exoplanet with structures that defy natural explanation. The universe has kept its deepest secrets hidden for billions of years. Now, armed with tools of unprecedented power, we're finally pulling back the curtain, and what awaits could be more extraordinary than anything we've dreamed. You don't need a PhD or a billion-dollar telescope to help unravel the universe's mysteries. Some of the most exciting discoveries happen because ordinary people, armed with nothing but curiosity and an internet connection, choose to look closer. Citizen science has become a powerhouse in modern astronomy, turning millions of volunteers into collaborators on projects that would otherwise drown researchers in data. Take the Zooniverse platform, where anyone can sift through images from the James Webb Space Telescope, classifying distant galaxies or tagging atmospheric features on exoplanets. In 2022, a retired teacher scrolling through galaxy images spotted a bizarre, elongated structure, a potential thread of dark matter visible only because human eyes caught what algorithms missed. That's the magic of collective curiosity. The more eyes on the data, the higher the chance of spotting the cosmic needle in the haystack. But classifying galaxies is just the beginning. Projects like Einstein at Home harness idle computing power from volunteers' laptops and smartphones to analyze gravitational wave data from LIGO, searching for pulsars hidden in the noise. Others, like SETI at Home, let you join the hunt for extraterrestrial signals by processing radio telescope data while you sleep. Even backyard astronomers are making waves. Amateurs using off-the-shelf telescopes have helped confirm exoplanet discoveries by monitoring stars for telltale dips in brightness, filling gaps in professional observation schedules. The universe doesn't care who makes the discovery, only that someone's paying attention. Funding advocacy is another way to fuel progress. Many groundbreaking missions, like the Hubble Space Telescope's successor, the Nancy Grace Roman Telescope, rely on public support to secure congressional budgets. Organizations like the Planetary Society lobby for increased science funding while offering tools to contact representatives or join letter-writing campaigns. When the public champions exploration, politicians listen after thousands voiced support. NASA's Perseverance rover included a microphone to capture Martian winds, turning a technical mission into a shared human experience. Engagement goes beyond data and dollars. Simply sharing the wonder of discovery can spark the next generation of scientists. Social media platforms are brimming with astronomers, educators, and enthusiasts breaking down complex concepts into bite-sized marvels. Follow researchers on platforms like Mastodon or Blue Sky, where they often share raw data or seek input on puzzling observations. Attend local astronomy club star parties, where a $200 telescope can reveal Saturn's rings or Jupiter's moons, connecting you directly to the cosmos. The most profound breakthroughs often start with a single question from someone who dared to wonder. Whether you're translating telescope data, advocating for science funding, or simply pointing out constellations to a friend, you're part of the story. The universe's secrets aren't reserved for those in lab coats. They're waiting for anyone willing to look up and ask, what if? And in that question, you're already exploring. Every revelation about the cosmos doesn't just add to our knowledge, it quietly reshapes what it means to be human. Consider how the simple act of pointing a telescope at Jupiter's moons in 1610 shattered the idea that everything revolved around Earth, upending centuries of doctrine. Today's discoveries carry the same weight, just on a grander scale. When we detect gravitational waves from colliding black holes or find water on distant exoplanets, we're not just collecting data, we're recalibrating our understanding of existence itself. One of the most profound shifts is the erosion of human exceptionalism. For millennia, we saw ourselves as the universe's focal point, but the more we explore, the more we realize how ordinary or extraordinary we might be. The Drake equation, which estimates the number of communicative civilizations, suggests we're either one of many or achingly alone. Both possibilities are equally humbling. If life is common, we're part of a vast, interconnected tapestry. If we're rare, then every star we see is a reminder of how fragile and precious consciousness might be. This duality forces us to confront uncomfortable questions. Are we stewards of something miraculous, or simply cosmic accidents adrift in an indifferent void? Yet these revelations don't just unsettle, they inspire. The same science that displaces us from the center also connects us to the cosmos in startling ways. Carl Sagan's famous observation that we're made of star stuff isn't poetry, it's physics. The iron in our blood, the calcium in our bones, all forged in supernova explosions billions of years ago. Modern telescopes have even spotted complex organic molecules in interstellar clouds, the building blocks of life scattered across the galaxy. Suddenly, the universe isn't just something we observe, it's something we're woven into, a story written in our very atoms. This interconnectedness sparks new philosophical movements. Cosmic perspectivism, for instance, argues that seeing Earth as a pale blue dot fosters planetary solidarity. Climate change, inequality, even conflicts, they all look different when viewed against the backdrop of a vast, uncaring universe. The overview effect, reported by astronauts who have seen Earth from orbit, describes this shift firsthand. Borders vanish, and what remains is a fragile oasis begging for cooperation. As space becomes more accessible, this perspective may trickle down to the rest of us, reshaping politics and culture in ways we can't yet predict. But the greatest gift of cosmic exploration might be its endless invitation to wonder. A child staring at Saturn's rings through a telescope is participating in the same awe that inspired Galileo, even if their understanding of the universe is light years apart. That continuity hints at something timeless: the human drive to look beyond the horizon and ask why. Whether we're decoding quasars or debating the ethics of contacting aliens, we're engaging in the oldest and most uniquely human endeavor, reaching for meaning in the dark. The cosmos doesn't offer easy answers, but it asks better questions. Every time we peer deeper, we're not just discovering the universe, we're rediscovering ourselves and the infinite possibilities hidden in the space between the stars. The greatest irony of science is this: the more we uncover, the vaster the unknown becomes. Every answered question cracks open a dozen new ones, each more puzzling than the last. Take dark matter. We've mapped its gravitational fingerprints across galaxies, yet its true nature remains just out of reach. Is it an undiscovered particle? A flaw in our understanding of gravity? Or something stranger still, a shadow of physics we haven't even imagined? The same paradox applies to consciousness. Why does a 3-pound organ made of ordinary atoms experience the taste of strawberries or the ache of nostalgia? We can pinpoint neural activity to the millisecond, but the leap from electrical impulses to subjective experience remains one of science's deepest enigmas. Then there's the universe's ultimate fate. Will it expand forever, galaxies dwindling into darkness as stars burn out? Or will dark energy's grip weaken, allowing gravity to pull everything back in a fiery, big crunch? Current observations favor eternal expansion, but with 95% of the universe's energy content still unaccounted for, we're like sailors predicting the weather while blindfolded. Even time itself hides mysteries. Why does it flow in one direction? Is the arrow of time an illusion, with past and future equally real in some higher dimensional framework? The equations of physics work just as well backward as forward, yet our lived experience screams otherwise. Some puzzles straddle the line between physics and philosophy. The fine-tuning problem, why the universe's constants seem improbably perfect for life, has spawned multiverse theories, religious interpretations, and everything in between. Meanwhile, quantum mechanics insists particles can be in multiple places at once until measured, forcing us to grapple with whether reality exists independently of observation. These aren't just academic riddles, they're cracks in the foundation of how we perceive existence. The beauty of these unanswered questions isn't just their mystery, it's their invitation. When the James Webb Space Telescope spotted galaxies too mature for their age, it didn't just upend cosmology, it handed us a new puzzle to solve. When lab experiments can't reconcile quantum mechanics with gravity, that tension points toward undiscovered laws. Even failures like the decades-long hunt for proton decay that keeps coming up empty tell us the universe is weirder than our theories predict. This isn't a failure of science, it's its greatest strength. The unknown isn't a void to fear, but a frontier teeming with possibility. Every generation assumes they're on the brink of solving it all, only to find the horizon receding, revealing new landscapes of wonder. And that's the thrilling truth. The universe isn't just stranger than we imagine, it's stranger than we can imagine. The journey isn't about reaching some final answer, but about perpetually widening the circle of light, knowing the darkness beyond holds discoveries waiting to rewrite reality itself. From gravitational waves humming through spacetime to quantum telescopes peering into the void, we've witnessed an extraordinary revolution in how we explore the cosmos. These aren't just incremental upgrades, they're radical new senses, letting us perceive a universe we were once blind to. Think about that for a moment. Humanity has spent millennia studying the stars, yet only in the past few decades have we discovered that most of the universe's matter is invisible, that space itself can ripple like a pond, and that black holes, once theoretical ghosts, collide so violently they shake the fabric of reality. And yet, for all we've uncovered, the cosmos retains its deepest mysteries like a cosmic poker player holding cards close. Dark energies accelerating push, the true nature of space-time, the possibility of other dimensions. These aren't just gaps in our knowledge, but chasms reminding us how much we have yet to learn. That's the beautiful paradox of astronomy. Every answer reveals deeper questions. When the James Webb Space Telescope showed us galaxies that looked too mature for their age, it didn't solve the early universe's puzzle, it handed us a new one wrapped in enigma. What makes this moment so thrilling is that we're no longer passive observers. With gravitational wave detectors as our ears, neutrino observatories as our fingertips, and AI-powered telescopes as our eyes, we're actively engaging with the universe in a conversation that's just beginning. The tools we're building today, quantum sensors that might feel dark matter's whisper, space-based interferometers that could spot wormholes, even proposals to use the sun itself as a gravitational lens, are rewriting the rules of exploration. So where does this leave us on the threshold, not just of new discoveries, but of fundamentally new ways to discover? The children of today might grow up in a world where finding alien life is routine, where hopping between dimensions is theorized, where we finally understand why the universe exists at all. And you watching this are part of that story. Every time you gaze at the night sky, share a science article, or even pause to wonder about our place in the cosmos, you're participating in humanity's greatest adventure. The universe has been keeping its secrets for 13.8 billion years. Now, finally, we're learning how to listen. What it tells us next could change everything. Drop your wildest cosmic theories in the comments below. Are we alone? Is time an illusion? What's beyond the cosmic horizon? And if you want to be here when the next big breakthrough drops, hit subscribe and ring that bell. The cosmos isn't done surprising us yet, and neither are we. The greatest discoveries aren't in our rearview mirror. They're waiting in the dark just beyond the edge of what we know.